Hello again. Let's finish this recap. Um, let's go down here to the tan of x, and now the limit as x goes to pi halves, and this is a minus sign right here. I'm sorry that's so hard to see, but this is a minus sign, and so we're coming at pi halves from the left. The limit as x goes to pi halves from the left of the tan of x equals positive infinity. But if you come at it from the right, you get negative infinity, where my cursor is now. So, hence, if we think about it in terms of inverse functions, if x goes to positive infinity of the inverse tangent, remember this is the arctan. And it's unfortunate, artifact of notation, -1 does not mean reciprocal here. It instead means inverse function. You just have to live with it. So the limit as x goes to positive infinity of the arctan of x is pi halves. Now here, we were taking a one-sided limit x going to pi halves. Here we're going toward one type of infinity and getting pi halves. Here we got infinity but went toward pi halves from the left. So it's kind of, we're just tying the inverse function in with the main function. So if x is inputted into the tangent, and if x is going toward pi halves from the left, we're going toward positive infinity. If x is inputted in my arctangent, then if x is going toward positive infinity, the arctan will limit toward pi halves. So this limit will equal pi halves. And in a similar fashion, x going to negative infinity will yield, will limit to negative pi halves, just as it's the sort of the opposite of this guy here, where x went to pi halves from the right, and we got negative infinity. But anyway, there's that. So, in any event, we get that. And you know what? Should this be, let's see, for the arctan, yeah. That's right. You know what? Actually, this it was sort of maybe not the best. This only piecemeal ties into this, because if we go at, yeah, this is correct, but notice negative pi halves. This is not negative pi halves here. This is positive pi halves, but we're coming at it from the left. This here really is negative pi halves, coming at it from the left to right, that only makes sense in the context of being in the limit here. At the end of the day, negative pi halves is just negative pi halves. This is positive pi halves, but coming at it from the left. This really is negative pi halves here. Watch out for that. So in a way, the example ties in beautifully here, or fairly nicely here, but not as good here, because this is pi halves, this is negative pi halves. So let's just take this as two separate problems. So let me separate these off. So the limit, there is some relation there. I'm not denying that. I just don't want to get caught up into stickiness. So the limit as x goes to pi halves from the left is this, and then limit as x goes to pi halves from the right is this. They're two separate infinities. Notice the overall limit as x goes to pi halves, it would not equal any kind of infinity. It wouldn't exist at all, not even in the direction context. Okay, and then let me separate that. Now, and let me get rid of hence. There is some relation, but hence is not really the word I want here. Let's just just remember from trig that the arctan will give you pi halves as we go toward positive infinity, and it will give me negative pi halves as we go toward negative infinity. Okay, so there's that. Now, okay, so the line x equals pi halves is a vertical asymptote of the graph of the tan of x. After all, we just needed one of these. As x goes to pi halves, let's say from the left side, we get positive infinity. So this right here, either one of these guys by himself, either this guy or this guy, let's just pick on this guy. So this is enough to establish that pi halves is a vertical asymptote. Now, why did I do this guy down here? We just need one of these. Let's just pick on this guy. Now, for the arctan, pi halves is a horizontal asymptote by the definition of the horizontal asymptote. For the ordinary tan, it's a vertical asymptote. So just be careful there. So it's a vertical asymptote for the ordinary tan, while, well, yeah, actually, I can pick on this guy too. Negative pi halves is also a horizontal asymptote for the arctan. You know what? I needed to look at both these guys because they don't yield the same thing. Never mind. You know, I just needed one of these, but I need to look at both of these because, you know, they yield two separate things. You know, to get a vertical asymptote, you know, it's enough that I either have just this or just this. I can have both. That's just a nice bonus. But since I had two different horizontal, if I leave this guy off, I'll be missing out on one of my horizontal asymptotes, namely negative pi halves. So negative pi halves is another horizontal asymptote for my inverse trig function. And, you know, I don't want to miss out on that, okay? So I would have missed out on another one of my horizontal asymptotes. Here I don't miss out on a vertical, but here I would have missed out on a horizontal. So just watch out for that. And so we get, now here's a quiz. Just using use substitution, do this problem on your own. Just go back to the previous video. Now here I give you a big hint. I almost give the problem away. Do this limit, big hint, almost a giveaway hint. Let u equal x squared. And now if u equals x squared, x is going to 0 from any side. U is going to 0 from the right side because u is always positive if it's not 0. So u goes to 0 plus of the sine u over u. And hopefully you know what that is by now. The number 1 should be screaming at you. Okay. And now for this, we also get 1 for an answer, but it's in a different way. I want you to break this off. The sine, and you remember sine squared of x really does mean sine of x, you know, sine x times sine x. You know, the negative 1 we abused it, but we don't abuse any other number. Like sine squared of x really does mean sine x times sine x. So you can break that off as sine x times sine x. So it's just the limit of it times the limit of itself. Hey guys, 1 times 1, guess what that is? Okay, now down here, and notice that since this limit tends to 1, 0 is not a vertical asymptote. This is that both of these produce a removable singularity situation. So 0 is not a vertical asymptote. X equals 0. And there's something you know what? There's something very dangerous I set up here, and I need to be careful. Wait, no I didn't. No, I'm perfect. No, I got it right. Y equals. Notice at vertical asymptote, it's x equals. I had it correct. Whew, thank goodness. So x equals pi halves, that's my vertical asymptote. You notice it's a vertical line, whereas y equals, this is a constant horizontal at one elevation, and here's a constant horizontal at another elevation. So, but anyway, there's that. Just making sure I had it right, and I did. Okay. So, if I had that wrong, I'd probably, that would not have been good, but anyway. So the limit x goes to 0 of this. Now the big hint is you want this to be x squared down here. You can think sine x squared over x can be thought of as sine x squared over x squared times x. So I break that up as the product of two limits here and here. The reason why I want x squared down here, because the sine of thing over the same thing, you know, I can work with that. I can do u substitution. I can let u equal x squared. Hey, that's just this guy up here. You know, and that limit is just going to be 1. And then this is going to be 0, obviously. What is 1 times 0, guys? That's your answer. So, that's good. Now this limit right here, the trick is to let u equal x minus 1. Now as x is going to 1 from either side, u is going to 0. So we just get this limit, sine u over u, and you should know what that is. It's not going to be shocking at all. Now this limit, now the answer is 0, but let me let the cat out of the bag. Note this limit was positive infinity, this limit was negative infinity, and guys, we define 1 over either infinity. You can define it to be 0. If you define it at all, you'd have to define it to be 0. So we define this limit to be 0. This one was kind of vague. If the limit of a function tends to either infinity, in particular, what the limit of a function tends to either infinity, even if the overall limit doesn't exist, but if the one-sided limits exist and tend to some type of infinity, then the limit of the reciprocal will tend to 0. So the answer here is 0 on account of that. That's what I mean. This one may be a little vague here, but that's what I mean. Now this limit is a little weird. you can think of this as 1 over, this guy right here is 1 over x times the numerator, the sine term, but x is going to infinity, so if we let y equal 1 over x, y is going to 0, okay? And in fact, it's technically going to 0 from the right side, so just to be, this isn't going to affect my answer one bit, but I do need to be a little persnickety, where y is going to 0 from the right, but it's not going to affect, the limit of, you just throw 0 into here, 0 times the sine of 0 is 0 all the way. So sine of 0 is 0 anyway. So that just washes away totally. It would have washed away even this y term here, even if this wouldn't have been 0, this would have been. But as it turns out, they're both 0. So anyway, the answer is 0. I went ahead and just did that one. You know, I thought about, well, will I make it a problem? Then nah. Now for this one here, limit as x goes to -2 of this, you just replace y with x plus 2. You could use u instead of y. It doesn't matter what letter you use. I just used y here. So y, you know, if x is going to -2, doesn't matter which side, then y is going to 0, and then you just get sine y over y, and we know what that is. And then in a similar fashion, now what if I cause a little bit of trouble? What if I put -x minus 2 down here? You have to yank out a -1, or just a negative sign. So we yank a -1 out to the side, and that causes this to become x plus 2 down here. I factored -1 out of this and made it x plus 2. And that -1 is right here now. But then, hey, we know how to handle this. We just do the uy, or the y substitution, u substitution, whatever you want to call it. And you just get, now it's going to be -1 because you got this negative dangling on. Now, guys, there's something, a little bit of, not abuse is happening. In some contexts, I'll let y equal a function. In this context, y is just a dummy replacement variable. I know that's a little bit abusive. It's kind of an abuse you may as well get used to. You're probably going to see it in your books and in your classes, okay? You may as well just get used to the abuse. Y does not mean a function here. It's just a dummy replacement variable. Okay. I know that's annoying, but it's an annoyance you kind of have to bear. Now, in a similar fashion, 3 minus x, I'd rather it be x minus 3, so I factor out a -1, which is just an understood negative sign. And so I just get the sine of this over this. I let u equal x minus 3. Don't forget your negative sign here. But otherwise, we know what this limit is, and we just stick the negative sign on the 1. Okay. And so there's nothing too earth-shattering going on here. Now, rational expressions, these are important. This is kind of the heart and soul, in a way, of the applied examples when we're doing the horizontal asymptote. If the denominator has a bigger power than the numerator, in this case it does, my denominator power is 3, my numerator power is 2, your horizontal asymptote will exist and it will be 0. So y equals 0 is going to be my horizontal asymptote. And you can take that to the bank, but you need to justify it though. Don't just put on the test, don't just put that, if you ever take a test or something, your professor will probably, unless he comes out and says otherwise, or unless she or he comes out and says otherwise, you will want to go in and justify your steps like this. You pick the highest exponent in the denominator. And when I did my other example, I was okay, I got away with it, but I should have been a little more specifying. You pick the highest exponent in your denominator, and in this case it's the only one, x cubed. And the highest, even if your numerator outdoes it, which it does not here, but even if it would have, we would still pick x cubed. So I divide top and bottom by x cubed here and here, and then you fragment like this. Then you simplify, like x squared over x cubed just leaves an x on the bottom, and x over x cubed leaves an x squared in the bottom, and then 9 over x cubed doesn't really change. Then you break apart the limits like this. Then you take out the multipliers, and then by the constancy takeout rules. But then, hey, the limit x goes to infinity of all these guys up top are 0. Now the limit x, this limit right here is just 1, but 6 times 1 is 6. So the 6 survives on the bottom. So we get 0 over 6, but that's 0. Remember, 0 over 6 is fine. That just equals 0. So y equals 0 is the horizontal asymptote of this original function here. Okay, you'll need to show your steps. I'm willing to bet, proverbially speaking, that you'll have to show your steps in class and on your tests. Okay. Let me see. When I said bet, I mean figuratively, not literally, you know. But anyway, now if they're the same, then your highest exponent on the top and bottom will be the same guy, x cubed. There's no ambiguity. So you go through the same steps as before. It's the same kind of problem, except I've got 4x cubed as my leader instead of 4x squared. That's huge, though. That one little change is huge. Because what that's going to amount to at the very end, I'm going to be left with 4 over 6, which reduces to 2/3 arithmetically. So y equals 2/3 is my horizontal asymptote. You do the same stuff, but notice this 4 survives because it was clothed by an x cubed. So y equals 2/3 is my horizontal asymptote this time for this particular function when I have a cube here instead of a square. Okay, now what if we go too good for our own good? Now this is no fun. If we overclothe 4, if I put a 4 here or a 5 here or a 6 here or a billion here, if I go above 3, the party is over. My horizontal asymptote doesn't exist. You know, I still might have a direction, and I probably will have a direction, but actually I will have a direction, but that's no fun. I wanted a horizontal asymptote. You remember, guys, to get a horizontal asymptote, you have to have a finite output in the end. And when the party is over, we get positive infinity. We can't have that for a horizontal asymptote. That won't work. So the limit x, so we do the same step. Now we divide by x cubed. We divide by the highest exponent in the denominator, not necessarily overall. Notice technically x to the 4th is my highest exponent overall, but I want the highest exponent in my denominator because that's where the trouble is. Getting a 0 on the bottom. But I go through the motions. I divide everybody by x cubed, just like before. But I get infinity up top, and I don't get infinity on the bottom. Guys, that's not going to flush away. There's nothing you can do. Your answer is infinity. Your horizontal asymptote does not exist here. The party is over. So it does not exist for this function, and there's nothing you can do about it. One thing I just now caught, this limit right here, this shouldn't have been positive 2. This should be negative 2. I didn't catch myself till late in the game on this one. Sorry about that. I just made an absent-minded typographical error. This is negative 2 right here where my cursor is, and not positive 2. I'm sorry about that. I just didn't catch myself. But otherwise, I had the concept right. You take out negative 1 and all that, and you get negative 1 in the end. Everything I said was right, except for this negative 2 right here. Well, I had a positive 2. Now it's correct. Negative 2 does go here. So I've got this corrected now. Sorry about that. And one other thing I wish I'd have pointed out that I just didn't point out. Y equals 2/3. It's enough, we've already shown that it's a horizontal asymptote. It's enough to just take it to whichever infinity you choose. Had we taken x to negative infinity, we'd have also gotten y equals 2/3. And for this guy up here, had we taken x to negative infinity, we would have also gotten y equals 0. And for now this guy down here, now had we taken x to negative infinity, we would have got a final answer of negative infinity right here, where my cursor is instead of positive infinity. We would have taken the limit x goes to negative infinity. But in any event, the horizontal asymptote doesn't exist. And really, on this one, I should have been more careful. I really do need to show that the limit x goes to negative infinity does not give you a finite answer in order to establish for sure that the horizontal asymptote is not there. And ultimately, it's true, it's not there. But I really should show this. So, thank you, and that really will be all.